Hello everyone. My topic is a survey of trends for binocular depth estimation. The content of my presentation contains 5 parts. The first is the goal of my research and the 3 main methods to the depth estimation and a conclusion. I set 3 goals. The first is have a broad understanding of depth estimation. The second is summarize disparity-based, CNN-based, and GAN-based binocular depth estimation. And the third is give some of my advice and opinions. So first, let me introduce you some depth estimation applications. How to obtain the depth information of the target is an important technical point in the current research and applications, such as industrial inspections and operation robots, autonomous driving, medical image diagnosis, face recognition, and 3D reconstruction. And many methods can be used to solve this problem, such as structured light, time of flight, molecular, binocular, and multi-beam camera. And among these, the binocular camera is the cheapest and universal option, so we choose binocular as our topic. So today I will talk about 3 different methods can use the binocular camera. The first method is disparity-based method. The flow of this method is listed. First, rectify the image distortion, and then extract the feature. After that, do feature matching, and then regularize the cost value. And we finally got the disparity map. And from this black and white picture, you can tell the distance of the depth from the pixel of the point. And the picture can also be multicolor. The right side of the slide shows a typical disparity-based depth estimation, and the right color here indicates the closed area, and the blue area indicates the furthest. Using this method has many limitations. For example, the first is the process from 2D to 3D may lack information, and the fusion results might go wrong. For example, like picture here, when it's convert from 2D to 3D, it may lose some information. And the second is the aerial lake texture. If the aerial has a few texture, the difficulty of the matching will increase. And the third is the limitation. The third limitation is the amount of computation. Is the computation complexity. And the fourth is handcrafted features. Since it's handcrafted features, so the flexible of this method is not enough. However, in the second method, convolutional neural network, extracting and matching features can be done automatically. Matching process often use an architecture named MCCN, and is kind of pseudo-Siamese. And put two patches from the left and right image. into the CAN to calculate through the decision network and got a score to see whether they are matching successfully. And then this slide shows many other derivative CAN matching structure. For example, adding per layer is an option, like in the left and in the middle structure. Some details can be ignored when come through the poor layers. Also, on the right, you can also design fully connected layers in your CAN. And this step will make you matching more details. And here are some classic implementations in CAN. The first one is MCCAN ARCT. In this structure, its common used structure contains 8 layers of CAN. And the other one is GCNet. GCNet uses shared weight Siamese network to calculate features and use information from both left and right features to calculate the cost value. Although CAN has the advantage of calculating features automatically, but also have many limitations, like the resolution is not high when sample data is not sufficient, or computing efficiency still needs to be improved when data is large enough. And there are too many designs of CAN, and the evaluation of the criteria is hard to choose. So we can to the last method using GAN. GAN is an end-to-end method, as shown on the slides. It first encoding and re-encoding the image space, and then decoding and re-decoding to get the depth image. We also use GAN to train the encoder and the decoder. The blue box here is a generator. And through this, we can get the depth image, the fake one first, and compare this one with the real image. So we can train the discriminator first, and then use the discriminator to go back to train the generator. Discriminator usually applies a pyramid structure. This process structure from coarse to fine will make the network more accurate and faster. And the GAN-based method, this is a design using GAN to do the depth estimation. The main idea is to list the left and right image. Left and right image side by side and as the input, and then we use CAN network and got the depth estimation. And the third one is the answer is the answer. So we can it's the real depth estimation. So compare the result and the answer. We can say that this project is this method works well and converges quickly. This is the method we implement in the other class 435, and I will show you some fundamental code. So this is our project in 435. And from here, we can see we refer other people's method and build the picture-to-picture class to make a generator here and made a discriminator. And the preview our image list as source image, generator image, and the destination image. So here is our input image. So here is the image we got, and this is the destination image. So like around 60 apples, we got here. We can see the discriminator loss and the generator loss, and you can tell the destination image and our image looks almost the same, and it converts quickly and works well. And back to our presentation, we can see that GAN-based method is in line with the trend of development, and there is also a lot of room for development and has good perspective. So first, GAN is more used to molecular, and little of this method are used in binocular. And the second, GAN method are most focused on the multi-level matching and seldom use a multi-level matching as post-smoothing task instead of feature extraction. And compared with other methods, GAN is more automated and more accurate. GAN can contain CNN method, and CNN can apply disparity method. At the end, here is a chart properties comparison. So from this chart, you can see the method properties of different methods. That's the end of my presentation. Thank you for listening.